Hi, my name is Ryan Thompson, and this is my milestone project for CPSC 5210. I'll be reviewing an article titled A New Graph-Based Method for Pair Work Alignment. Some background about this article points out that the background of this field before several papers did network alignment to, with the aim of studying conserved network topology. And so what they were getting at with the conserved network topology is an idea of network experiences a change or is a change that change will effect on the different connections, and the connections that remain after the stimulus has been applied are meaningful, right? These are strong, almost like a Darwinian view that the strongest connections have survived the change and are useful post-change. So that is the idea, as I've understood it, on conserved network topology, and why this is why this paper or this line of analysis is useful in the field. Heuristics previously were used to approximate alignment scores. So let's talk about that. The heuristic is just a simple back of the envelope calculation meant to approximate a more in-depth calculation. So instead of using a full method, the heuristic provided just a faster means to calculate, probably one that they could define a full runtime on. And the alignment score is how do these edges connect, or how are these edges related to each other via connected after the stimulus has been applied. So if you have graph 1 and graph 2, how do the edges correspond to each other? And how would you apply some type of quantitative value to those connections to be able to say how similar two graphs are after a stimulus has been applied, for example? But it doesn't have to just be a stimulus. It can simply be two networks that you want to compare, and you have some idea of the relationship connection between different edges that exist to each individual graph. Previous work restricted single node and not a global alignment. So when it says a single node, that'd be an individual vertex and not edges. And it would be talking about just a realization or an actual edge connection, and not the potential for every edge that existed between the two graphs and what that really means. So previous work was very specific focused, and this work tries to generalize it a step more, not a complete generalization, just a step more. So it goes from single node to pairwise matches, which forms an edge. So that's the background on where it was, and that will help set the stage on why the methods or procedures are in place that make this a new paper. So we're going to review some important concepts in the paper that are fundamental to it. Of course, the runtime is an important component of this, because any searching algorithm, or really kind of a branch and bounded concept, is really interested in what is the runtime, because many of them will end up calculating along the same line, but the question is how fast, or what are the bounds that you can collectively prove that your algorithm will operate inside of. So the authors classified and backs up this classification as NP hard. So right from the article's text, the author reduces the problem the algorithm is trying to solve through, and maximum common subgraph is a common subgraph with the maximum number of edges, and its computation is well known NP hard. And then the author references other works inside the paper that classify different types of NP completeness. So NP stands for this non-deterministic polynomial acceptable problem. So given that this is an NP hard problem, there's not really a known runtime for this, and that would be a substantial improvement in the field to be able to classify NP hard problems and give a bounded time frame for them. So given that it's NP hard, this computation has to use this algorithm has to use other methods to for termination. So you aren't able to necessarily prove a given time, you're not able to prove exactly a given time, but you're able to give certain termination criteria, and then the program will terminate itself. I think other NP hard problems are very large traveling salesman problems. Those are other ones where the solution can be found given enough time for it to run, but there's not necessarily a bounded time for it. Another important concept is the idea of this Lagrangian relaxation. So relaxation itself is a Lagrangian, to define it a little clearer, a Lagrangian relaxation of a complicated problem and combinational optimization penalizes violations of some constraints, allowing an easier relaxed problem to be solved. So this penalty function is essentially an eigenvalue problem, and inside this penalty, which is an individual eigenvalue for whichever linear inequality is being relaxed, as that eigenvalue changes, or the relationship between the eigenvalues for the different inequalities change, you'll wind up with different. And so you're always looking for which eigenvalue combinations on different inequalities close the bounds as tight as possible. So this method is really encompassed under Lagrangian relaxation, is a relaxation method which approximates a difficult problem of constrained optimization by a simpler problem. So our constraints represent the different linear inequalities that we'll have to set up to solve this problem. A solution to the relaxed problem is an approximate solution to the original and provides useful information. So approximate is the key word here, because you're coming up with an upper and lower bound, and this is defined as a duality gap. So the dual gap between where is your optimum answer and where could the optimum answer be on the high end, and where could the optimum answer be on the low end, and theoretically the true optimum answer lies in the middle somewhere between them. And that's kind of the principles of Lagrangian relaxation, is that you know for certain that the answer is somewhere between the two bounds. Now hopefully you can close the bounds in with some reliability that you're comfortable with those estimates. But again, the Lagrangian relaxation is an approximation and still does require substantial computation time. So another important concept is the paper's addition to the field, and we'll talk about scoring functions in a few slides, but the introduction of maximum structural matching formulation for global network alignment and show its relation to the global alignment graph. So that's quite a bit to say. Here is this score for matching. And what it's saying here is it's going to look over an edge in graph 1 and all edges in graph 2 and determine if they're realized. And if they're realized, they get a score of 1. And if they're unrealized, they get a score of 0. So it starts here, for example, where it says AB. Now, AB is connected. A is connected to big A. Is big A connected to another connected graph, C? So AB, AC are two edges that are connected through at least one vertex, or through the vertex. So that will give it a score. Now, the goal of this is to calculate the maximum potential matching for it. So it's quite a large problem. And as you go through and create these inequalities, that's what you're applying the eigenvalues to relax them, so that if they're violated or their emphasis is de-weighted, so that you can hopefully solve it a little faster. So this is what the scoring function comes out to be, or the matching function does, but at the root of this is truly a scoring function between the connectiveness. So up here would be graph 1, and here is each vertex of B1, which makes up G1, and each of these curved lines represent an edge that is an element of edge 1, which is part of graph 1. And that same notation will, of course, apply down here. Now, we'll see in the next slide what does a scoring function between these two graphs really look like, and how can we actually get a value out of this? So we're going to walk through the example here. So the matching algorithm is actually just a generalized form of the alignment algorithm that the author outlined. So here's the alignment algorithm, and this is really broken down into two parts. You have your first for your internal score, how connected is graph 1 to itself, and then you have your connectiveness between graphs. So here, how much is each vertex connected, and here is how are the edges between each graph connected. So we're going to let G1 and G2, they're going to be two distinct graphs, independent of each other, but connected in some way. So A of I equal J indicates that for alignment I, it is connected to J such that I is an element of V1 and J is an element of V2. So I, say the first one is A, it is connected to J. So A of I1 is J1. Now this sigma function here relating the connectedness is this score. How is A connected to here? So for sigma I, it's connected to J, and that's a true connection. So it'll get to 1. Now A2, so if I is still 1, and this goes to A of 2, which you say is B, that is not realized, so it'd get a 0. And then you're going to end up summing here. You'll sum over all the vertex connections. Once you've gotten a score for the vertex connections, you'll get a score for the edge connections. And so IK, say A is I and B is K. And we're looking at where are those connected. So what other points are those vertex connected? That's A here, as outlined before, and A of K, which would be C here. And that would get a 1. So what it says is we have an edge, and the vertexes of that edge are also connected to an edge whose vertexes are also connected. Back. So again, here's the formulation. Indicates that a vertex in the edge is connected to a vertex in the graph of the edge of the other graph. So tau, I, A of I, K, A of K is equal 1 if it's realized. So if basically for an edge you have two red lines in this diagram, then it receives a score of 1, or else it's 0. So just to kind of concrete this example a little more, given this scoring function above and this graph here demonstrated, we're going to calculate the scoring alignment for this graph. And again, remember the matching alignment, the global matching, is just a generalization of this if you were to hold sigma equal to the interconnectedness of the edges. So we'll go through this one example, and this will, since it can be generalized later, this is, I think, a more thorough example. So here's sigma A, B, C, D, B, E, D. So those represent how each vertex is connected. So for each red line, you get a score of 1. And then you sum the red lines, so you get a score of 4. Now tau asks if you have an edge and each vertex in that edge is connected to another realized edge in the second graph. So AB is connected to AC because AC is a true connection. and then you have AD, and so on here, and you wind up with 5. Yeah, that, yes. So changing this function, or changing this relationship on the graph, would change this below scoring function. But here, A and C should be related to be valid for this below graph. So you can see the connectedness here is quite high, and it only grows. The computational aspect of this only grows. So once you have sigma calculated, and once you've calculated this dual summation over each edge in graph 1, looking for potential realized partner in graph 2, you get a score of 5. Then you'll sum the vertex connection score and the edge connection score, and that's how you get a score of 9. So you would take this score, and then you could look at how that alignment score compares to other alignment scores for graph 1. And that would be a procedure that you could do to evaluate different networks that you found, or other networks that you have a bank stored in, to go forward. The procedure. So I've given an overview of just a straightforward score alignment to calculate, with not that many nodes in each graph. But in general, what is the procedure to do this for an extremely large vertex? So we would take the original equation, the scoring alignment, and we'd reformulate it or generalize it to the matching algorithm, again by just setting the internals equal to the edges, or the vertexes equal to the edges, and we would just formulate each of those as a linear inequality. Then we would have to assign, because it's an NP hard problem and you don't know how long you could be sitting there, you would have to assign a termination criteria. So the paper suggests some type of runtime limit. So if you wanted to say, give me the optimal score after running for an hour, or give me the Lagrangian relaxation score after running for an hour. So it will provide an upper and lower bound for that matching a lot, for the scoring matching after an hour. So that's our termination criteria. Then we would execute the algorithm, and we'll review some pseudocode for that in the next slide. And as the algorithm is executing, it will apply the Lagrangian relaxation technique throughout, while it hasn't met the termination criteria. And then once the termination criteria, say an hour has passed of runtime, you'll examine the duality gap after termination criteria has been reached. So again, the duality gap would be the distance between the upper and lower bound, with, again, the theory stating that the optimum value should be between the duality gap. So hopefully you've gotten that bound tight enough that you feel comfortable going forward with it, to say that the bound exists plus or minus this much, potentially. So the big steps here is to use linear optimization, because we have a set of linear inequalities, and integer programming that's makes it even faster, because we're using ones and zeros, and we're not having to use mixed integer linear programming or anything a little more complicated than that. And then we assign termination criteria, because NP hard problems don't necessarily allow you the ability to derive the runtime from the algorithm. Then we would execute it, and we allow it to apply the relaxation techniques, and allow the termination criteria as an overarching constraint for the process. So here's an overview of the algorithm pseudocode. This is directly from the paper, so this is outlined in terms of the author's mindset. So you'd initialize the code, which is read in the two graphs in the graph ML format that the author states is, I guess, a standard in the field. And initially you set your lambda to 0, which is our penalty function, and you set your upper bound to positive infinity and your lower bound to negative infinity, obviously creating the most extreme bounds. Then you'd run your search algorithm and keep repeating to derive the score. So you'd run the matching score. You'd run this matching algorithm for the main loop, and then you would repeat. And once you've gone through that given a penalty function of 0, you would adapt the Lagrangian multiplier to some other value, and then you would recompute the main loop. And you would evaluate how did the new upper bound, compare to the previous. So after the first iteration, of course, it's going to be less than infinity. So that will take on a new upper bound. And if the lower bound is greater than the lower bound that's initially set, which it will be to begin with, it takes on the new lower bound. And then it takes on what the x and y's are. So again, x is the solution of the relaxed problem. And obviously you're storing these solutions as you're going on in time. So I'm sure another termination criteria is if after 3 iterations in a row that the band hasn't tightened into a certain tolerance, you haven't gotten 1% better after 3 iterations, terminate and move on. That could be another criteria. And so until the lower bound equaled the upper bound, which would be the ideal goal, but you don't know how long that would take to run. So in some cases, you just don't do that. And you give it the termination criteria of a % difference between iteration 1 and iteration 2, or you give it just a total runtime to go after. So once that termination criteria is met, the program executes completely. So this is what kind of a pseudocode would look like. And obviously each time you're having to go through and check, is the upper bound less than? If so, take that. If the lower bound is better than, take that, and then record the x and y values, depending if you're going to record that score or not. So you'll get an idea if the Lagrangian or if the eigenvalues have changed in a significant manner. Oh, again, just to point out that this pseudocode that's outlined is expected to run on an integer linear programming problem. So any adaptations or any scoring functions need to take that into account, and you couldn't use any fuzzy logic, or if you use the fuzzy logic, that'd only add to the runtime complexity. So you would have a risk issue. You would have a wider range for the upper and lower bounds. You have a larger duality gap. So we were asked to highlight what are some of our own contributions or our own thoughts or musings after reading this paper and looking at it. So I have 2 areas of further areas of investigation that I think would be warranted after reading this paper and looking at some of the other topics that the author cites. So the first would be in-wise matching, and so this is a play on the author's paper of pairwise matching. So he assumes 2 vertexes are connected to make the edge. While that obviously is important because it's a step further than just single node interactions, I would ask, can we generalize the code to account for more than just the pairwise matches? So whoever is investigating the graphs allowed the investigator to specify the number of combinations up to minimum whichever graph has the lowest number of vertex. So if one graph has 10 vertexes, you can say up to 10, but not exceeding the minimum, whichever the minimum is here. And the reason that I think that this would be interesting is this will provide additional insight to the conserved network topology and what interactions are useful. So obviously, knowing what nodes are connected are helpful, but knowing what pairs of nodes are helpful. But if the investigator was able to say, I want to know for a 3 combination or a chain of 3, how does that matching still, is that matching conserved between a stimulus applied between networks? And I think that would be helpful because as you examine more and more interactions, if you see a few chains pop up with a common, I think you have the ability to spot a higher commonality of a vertex between graph 1 and graph 2, between the conserved network topologies, because you would have it identified and then you'd be able to flag it for its like its frequency count of how many times it's being observed. But you would be able to flexibly look at that. Maybe examine the duality gap for pairwise and then examine a duality gap per se 4. So how are 4 vertexes creating an edge connected, and is that conserved? So I think that allows you some framework, especially in networks that are like highly redundant. I think that would be helpful. And some downfalls of this is this would increase the number of linear constraints, but functionally the procedure and the pseudocode outlined previously wouldn't drastically change. I mean, you'd still have the eigenvalues and go through and really examine a duality gap between your upper and lower bound, and really have to rely on termination for percent change or runtime, saying only run for an hour and then cut off. But it would, again, give you the ability to potentially ask, are longer chains conserved or are shorter chains conserved between the conserved network topology? And I think that would be interesting to note, is if there truly is a difference and if long or short chains are conserved or broken between the stimulus being applied. Second area of investigation that of my own thoughts that I thought this paper stimulated that other people could look at are connectedness distributions. So what the steps for this would be to calculate the number of internal edges to a graph, assuming it fits the definition of connected. So definition of connected is that every vertex can get to every vertex can get to every other vertex. So you would take the number of vertexes and raise it to the number, and then once you have that, you've got the maximum connectedness, right? You've got the score for connected. And then you calculate for that graph the number of internal realized edges. So you have what connections are actually existing, and then you look at the ratio between realized and the number of potential connections. So realized over potential, and then you record this. And you create a distribution of that ratio that can be used for modeling the effect to a network change. So the goal here in my framework is to take this ratio of potential to realized and have a distribution of which that you can look at the covariance between this alignment score that the author calculates and the internal changes. So if you apply stimulus to this topology and the internal number of connections change or break, you'd be able to record that. You would know how the potential inside changed from one measure to the other, how this ratio changed. And then you know the alignment score. So with enough samples between networks, alignments changing, right? This global matching changing between graphs, and how internally the graph changed itself, you could calculate the covariance between those two measures. And if you come up with a strong covariance between them, you could potentially use it as a screening tool to limit networks that you don't think would be candidates to run these large algorithms over. So again, the way that it would work is you have a distribution reflecting the ranges of interconnectedness after a single stimulus has been applied. And then you also have a distribution of alignment scores of the maximum alignment or maximum matching between graph 1 and graph 2. So either the graph post-stimulus to pre-stimulus or post-stimulus to a different baseline graph. And then once you've gotten the covariance of enough samples to say, how does the internal change of the stimulus relate to its connectiveness to another baseline graph, you could use it as screening. So you may not have to constantly rerun to say how is the overall matching scheme. You would say that we could expect with a certain probability that given this ratio shifting to a different percentile, it's maintained its matching or it hasn't maintained its matching. So it gives you an idea of how interconnected were we before to now without having to fully rerun this alignment, but you would need to have enough sample data. So you're really evaluating the stimulus, the response of the stimulus between the graphs, and then you're also evaluating uh, the graph itself to other graphs. So see how that change is applied. So I think this one's very interesting and has some potential, but you very much have to watch out for uh, a sample power. And so I think you would need to really look at how many graphs are out there that you're going to compare to and what is the power or the sample size I would need to have a stable covariance measure so that I could apply the stimulus, look at the graph's interconnectedness to itself pre and post, how are those vertex connections changed, and then say, do I need to calculate an alignment score or not? If it's a high covariance, you may be confident enough that the alignment's going to hold and you could go forward, or if the covariance has gone down enough, maybe you could throw it away. So it would really help identify that middle ground that you could help really create a more robust sample. And then before, there were a couple of references. One, pulling some direct quotes from the paper, and then two, some of the relaxation and Lagrangian relaxation from the Wikipedia sources. So again, the further area of investigation or my own contributions after reading the paper on in-wise matching. So how are long or short chain connections conserved between a stimulus or a change applied between network topology? And this connectedness distribution, which looks at how did a graph internally change, and then could you derive the probability that the alignments hold between graphs? So do the edges still maintain their connections pre and post, and coming up with a covariance value to say if they do or do not. Again, this paper reviewed Clow's new graph-based method for pairwise global network alignment. Thank you.